Hi everyone. Today we will discuss rotational spectroscopy, microwave spectroscopy. Okay. So we know spectroscopy. Spectroscopy is the study of interaction of electromagnetic radiation with matter. Spectroscopy is the study of interaction of electromagnetic radiation with matter. So by using spectroscopy, okay, we can get various information like bond lengths, we can calculate bond angles, what are the various functional groups present in the given molecule. If you go to NMR spectroscopy, proton environment, okay, structural elucidation. Spectroscopy is useful in the structural elucidation. So bond lengths we can calculate, bond angles, geometry, okay, all those information we can get from spectroscopy. So in that we will concentrate now on rotational spectroscopy or microwave spectroscopy. So before going to that, one more concept important, that is Lambert-Beer's law. Lambert-Beer's law. Okay, I will explain briefly in the examination point of view as you have less time. Okay, Lambert-Beer's law. You know, according to Lambert-Beer's law, absorbance is equal to epsilon Cl. That means absorbance is directly proportional to concentration and path length. Okay, for example, we are passing radiation whose intensity is I0, intensity of incident radiation is I0, passing through the sample. Okay, this is sample holder. Let us consider the length of this sample holder is L or cuvette. It is called cuvette, length of the cuvette, or it is called as path length. L is called as path length, and some amount of radiation is absorbed by the sample that we are taking as IA, and the remaining is transmitted, that I am indicating as IT. So that means IA is not nothing but what? I0 minus IT. Intensity of radiation absorbed is incident radiation intensity minus transmitted radiation intensity. Okay. So absorbance depends on what? Concentration of the solution we are taking here. As the concentration of the solution increases, absorbance also increases. And as the path length of increases, cuvette increases, absorbance increases. So this is Lambert-Beer's law. Now here epsilon is called as what? Molar extinction coefficient. Molar extinction coefficient. Or absorptivity, that is also called as absorptivity. Okay, if the concentration is 1 molar and path length is 1 centimeter, concentration is 1 molar and path length is 1 centimeter, then whatever the absorbance we are getting, that is called as epsilon, absorptivity. For a given concentration, for a given path length, what is the absorbance? That is called as molar extinction coefficient or absorptivity. It explains how strongly a given substance absorbs a given radiation, given wavelength radiation. How strongly a given substance absorbs the given radiation. So it is a characteristic of given substance. Epsilon is a characteristic of given substance. So what is the unit for epsilon? Epsilon is equal to what we have? A by Cl. Absorbance has no unit. Absorbance has no unit. So C inverse, L inverse we are getting. That means M inverse, centimeter inverse, or liter per mole per centimeter. Liter per mole per centimeter, that is the unit for epsilon, that is the characteristic of given substance. So some more expressions if you see for Lambert's-Beer's law, absorbance is equal to have epsilon Cl. Another expression is log I0 by IT, log I0 by IT, or if you take transmittance, I am indicating as a T, Transmittancy is nothing but that is the ratio of intensity of transmitted radiation ratio to intensity of incident radiation. So transmittancy is given as IT by I naught. Here we have I naught by IT. So if you write it as IT by I naught, we will get minus. So minus log IT by I naught. IT by I naught can be written as transmittance. So another expression is minus log T. Next one, percentage of transmittance. Percentage of transmittance means transmittance into 100. That means IT by I naught into 100, that gives percentage of transmittance. So from this, T can be written as percentage of transmittance by 100. So another expression, if you see, okay, log T we can write as log percentage of T by 100. So log A by B, log A minus log B, so log percentage of T minus log 100. Log 100 means log 10 power 2, that is 2. So log percentage of T minus 2 we are getting. That means minus log T we can write as what? 2 minus log percentage of T. So these are the various expressions we have for absorbance. Absorbance is also called as optical density. Absorbance has no unit. Absorbance has no unit. You may remember these expressions. Absorbance is equal to epsilon CL log I naught by IT or minus log T or 2 minus log percentage of T. Okay, so from this log IT by I naught is equal to what we get? Minus epsilon CL. Okay, if you take reverse and here we will get minus epsilon CL. So IT by I naught is equal to 10 power minus epsilon CL. So this is the expression for fraction of radiation transmitted. Once a question given like this. What is the expression for fraction of radiation transmitted? This is the expression for fraction of radiation transmitted. Then what is the expression for fraction of radiation absorbed? So total it is 1. So therefore fraction of radiation absorbed is 1 minus 10 power minus epsilon CL. This is the expression for fraction of radiation absorbed. This is the expression for fraction of radiation transmitted. Okay. Next one, if you have two samples, okay, sample 1 absorbance is A1, sample 2 absorbance is A2. Then if you take sample 1 plus sample 2 mixture of these two samples, then what about absorbance? If you take mixture of these two samples, the absorbance is A1 plus A2. Sample 1 absorbance A1, sample 2 absorbance A2. Then if you take mixture of these two samples, absorbance is A1 plus A2. Next one, we are taking same sample, but we are recording, okay, same sample means epsilon is same. We are recording at C1 concentration and C2 concentration and at L1 path length and at L2 path length. Then, okay, if at one concentration and path length is known to us, at another concentration and path length, we can calculate absorbance by using this expression. A1 by A2 is equal to C1 L1 by C2 L2. Or we can write as minus log T1 by minus log T2, minus minus gets cancelled. Or we can write as 2 minus log percentage of T1 by 2 minus log percentage of T2. Based on the data given, we have to follow. Okay, so at one concentration or at one, if one transmittance, at one transmittance absorbance is known to us, at another transmittance absorbance we can calculate by using this equation. So these are some expressions you may remember from Lambert's-Beer's law. Next one, before going to rotational spectroscopy or microwave spectroscopy, we have to see what is the classification of molecules based on moment of inertia. Okay, classification of molecules based on moment of inertia I. Moment of inertia is indicated with I. So moment of inertia indicates what? How easily a molecule can be rotated with respect to an axis. How easily a molecule can be rotated with respect to an axis that is indicated by moment of inertia. If you take a single body system, the expression is mr squared. If you have many bodies, okay, then this is the expression for moment of inertia. I is equal to summation I mi r square. Okay, if you take a two body system, diatomic molecule, for example, if you take a two body system or diatomic molecule rigid rotator, the expression for I is m1r1 square plus m2r2 square, but that if you simplify, finally we will get mu r square. Okay, for two body system, what we will get actually m1r1 square plus m2r2 square, but if you simplify that, finally we will get mu r square for diatomic molecule. Mu is called reduced mass. How to give reduced mass? m1 m2 by m1 plus m2. Okay, you remind, while we are calculating reduced mass, we have to substitute mass of only one particle in it. That means we have to substitute in atomic mass units. For example, CO 12 atomic mass units, oxygen 16 atomic mass units. Like that we have to substitute in. One atomic mass unit is equal to 1.66 into 10 power minus 24 grams or 10 power minus 27 kgs. Okay. So this is the expression for diatomic molecules or rigid rotator. Okay, this is the expression for moment of inertia. Okay, if mass increases, it shows more restriction to rotating. As length of the particle increases from center of gravity. Okay, here 1 kg is attached, here also 1 kg is attached. Mass is same, but here length of the distance of the particle is increasing from center of gravity. Whenever the distance of the particle is increasing, it shows more restriction to rotation. So second one shows more restriction to rotation. Okay. Now here we are taking same length. Here the distance of the particle from center of gravity 1 centimeter, here also 1 centimeter, but here 1 kg we are taking, here 2 kgs we are taking. So second one shows more restriction to rotated. Second one shows more restriction to rotate. So how easily a body can be rotated with respect to an axis that we can give based on moment of inertia that depends on mass and distance of the particle from center of gravity. Okay. For example, if you take CO2, during rotation, okay, here we have center of gravity. So during rotation, the center of gravity position cannot be changed. So carbon position cannot be changed. That means carbon can consider as stationary. Carbon can be considered as stationary. So therefore, I is equal to, here we will get m r square. Okay, oxygen position changes plus mass of oxygen atom, distance of oxygen atom from center of gravity. Distance of oxygen atom from center of gravity means that is nothing but CO bond length. So mass of oxygen atom, okay, for this bond and for this bond. So we'll get I is equal to what? 2 into mass of oxygen atom, bond length of CO over 2. Like this we can calculate moment of inertia for CO2 molecule. CO2 molecule, if you take center of gravity is nothing but where the masses are balanced from all the directions. So at carbon, masses are balanced. So at carbon we have center of gravity. During rotation, center of gravity cannot change. Okay, so carbon is considered as stationary. Only oxygen atoms positions changes during rotation. So therefore, for this bond we will get MORCO square. R is nothing but the distance of oxygen atom from center of gravity, that is nothing but C double bond O length, bond length. So like this we can calculate moment of inertia for CO2. This is the concept of moment of inertia. So moment of inertia is a vector quantity, it depends on direction. So it has 3 components. Moment of inertia has 3 components along x direction, y direction and z direction. I am indicating as IA, IB, IC. Okay, moment of inertia has 3 components along x, y, z directions. Those 3 components I am indicating as IA, IB, IC. So based on these IA, IB, IC, molecules are classified into 4 types. Based on moment of inertia, molecules are classified into 4 types. The first one is linear molecules. Linear molecules. For linear molecules, IA is 0, IB and IC are same. So just you remember this. Linear molecules, IA is 0, IB is equal to IC. Okay, the examples, for linear molecules, easily you can identify H2, N2, O2, CO, etc. All these are linear molecules. Okay, the molecules generally belongs to C infinity V point group and D infinity H point group. Those corresponds to linear molecules. What about moment of inertia? These conditions you remember. IA is equal to 0, IB is equal to IC. Okay, the conditions are important. The second one is spherical top molecules. Spherical top molecules. For spherical top molecules, the moment of inertia is same in all the directions. IA is equal to IB is equal to IC. The examples are the molecules belongs to tetrahedral point group and octahedral point group. Okay, the molecules belongs to tetrahedral and octahedral point group. Here linear molecules means acetylene. Those also will get it. Polyatomic molecules, acetylene, etc. Okay, spherical top molecules means molecule belongs to tetrahedral and octahedral point groups. That is CH4, CCl4, NH4 plus. Okay, UF6, okay, UF6, SF6, okay, etc. Icasohedral point group, that is C60 fullerene, also comes under spherical top molecules. Sphere means all the directions are same, so we will get moment of inertia same in all the directions. IA is equal to IB is equal to IC. Okay, these are some examples which follow this condition. IA is equal to IB is equal to IC. The third one is symmetric top molecules. Symmetric top molecules. The moment of inertia lies. IA is not equal to 0, IB is equal to IC. See the difference between linear and symmetric top molecules. In the case of linear molecules, moment of inertia is 0. IA is 0, but here IA is not equal to 0. But IB is equal to IC. The examples, generally the examples belongs to C3V point group and D3H point group comes under symmetric top molecules. For example, BX3 or BCl3, CH3Cl, methyl chloride, methyl bromide, methyl fluoride, CH3Cl, CH3Br, etc. NH3. Okay, Ylene also comes under symmetric top molecules. Ylene, generally the molecules contains Cn where n is greater than 2 rotational axis. Here if you see C3 rotational axis is present. Okay, those molecules comes under symmetric top molecules. Okay, what are the examples? Methyl chloride, methyl bromide, ammonia, Ylene. Those are examples for symmetric top molecules. And last one, asymmetric top molecules. Asymmetric top molecules. If moment of inertia is not same in all the directions, IA is not equal to IB is not equal to IC, then that is called asymmetric top molecule. The examples are generally the molecules belongs to CS point group and C2V point group comes under asymmetric top molecules. For example, H2O comes under C2V point group, H2O, SO2. Vinyl chloride comes under what? CS point group. Okay, those are examples for asymmetric top molecules. Naphthalene comes under asymmetric top molecule. Okay, examples are H2O, SO2, vinyl chloride, naphthalene, etc. comes under asymmetric top molecules. So now I am going to pure rotational spectroscopy. Pure rotational spectroscopy or microwave spectroscopy. Pure rotational spectroscopy or microwave spectroscopy. So the name itself indicates here which radiation we use. We use microwave radiation. We use microwave radiation. Now what happens whenever we are applying microwave radiation on given sample? Okay, so whenever sample interacts with microwave radiation, which type of transitions occurs in the molecule? Rotational transitions occur in the molecule. Since this energy is not sufficient for vibrational transitions or electronic transitions, the microwave radiation energy is small, so that is sufficient only for rotational transitions. Only pure rotational transitions occurs. That's why it is also said to be pure rotational spectroscopy. Only rotational transitions occurs, okay, or transitions occurs in between rotational energy levels. And to record microspectra, we have to take sample in the gaseous state. Sample should be in the gaseous state. So in the gaseous state, the interactions between the molecules are very, very low. As the interactions between the molecules are low, we take sample in the gaseous state. In the liquid state or sample state, the molecule cannot undergo free rotations. Interactions are high. But in the gaseous state, the interactions are low, so the molecules can undergo free rotation. That's why generally sample we take in the gaseous state. And what is the condition to show microspectra? This is important. What is the condition required to show microwave spectra? The condition is the molecules have to possess permanent dipole moment. The molecules have to possess permanent dipole moment. So the dipole moment of the molecule should not be equal to 0. They have to possess some net dipole moment. For example, if you take homonuclear diatomic molecule, homonuclear diatomic molecules, H2, N2, O2, whether all these possess permanent dipole moment or they do not possess permanent dipole moment. They do not possess permanent dipole. Same atoms are there, electronegativity is same, so no electronegativity difference, no formation of dipoles, okay, no formation of partial positive and negative charge. So homonuclear diatomic molecules are said to be microwave active or inactive. They are microwave inactive. They do not show microwave spectra. So the information regarding bond lengths or bond angles, okay, and isotopic mass, such information we cannot get based on microspectra for homonuclear diatomic molecules. Okay, by using microspectroscopy, which information we can get? We can get information about bond lengths, bond angles, isotopic mass. We can calculate. Okay. Now, if you take centrosymmetric molecules, the molecules having center of inversion. The molecules having center of inversion. For example, acetylene. It possesses center of inversion or not? Yes. CO2. Centrosymmetric linear molecules. Centrosymmetric linear molecules. Just for centrosymmetric linear molecules. For example, trans 1,2-dichloroethylene. Trans 1,2-dichloroethylene. If you take, what about net dipole moment for all these molecules? Net dipole moment is 0. All these are centrosymmetric molecules. All these possess center of inversion. So for all these, net dipole moment is 0. Okay, dipole moment is a vector quantity. Left side +5, for example, right side -5. So net dipole moment is 0. Here also same. Net dipole moment is 0. So how can you differentiate cis 1,2-dichloroethane, trans 1,2-dichloroethane? That is given previously, and we can differentiate trans 1,2-dichloroethane and cis 1,2-dichloroethane based on microspectroscopy. Trans 1,2-dichloroethane is microwave inactive. So all these are microwave inactive. They do not possess net dipole moment. They do not possess net dipole moment. So all those are microwave inactive. Centrosymmetric molecule. Next one, if you take spherical top molecules. Spherical top molecules already we discussed. The molecules belongs to tetrahedral point group, octahedral point group. Okay. Whenever we are taking sphere, and sphere, if you do rotate, sphere if you undergoes rotation, is there any change or no change in it? No change in the shape, no change in the geometry, or no change in the coordinates. So spherical top molecules are also said to be microwave inactive. CH4, CCl4, okay, all those are said to be what? Micro inactive. SF6, UF6, okay, those are micro inactive. So what are the examples for micro inactive substances? And homonuclear diatomic molecules, centrosymmetric molecules. Next one, spherical top molecules are examples for microwave inactive substances. Which are microactive ones? For example, heteronuclear diatomic molecules. If you take heteronuclear diatomic molecules, for example, HCl, NO, HBr, CO, etc. They possess some permanent dipole moment. Electronegativity of both the atoms is not same. So mu is not equal to 0. Okay. So they are said to be microwave active. So you just remember what are the examples for microwave inactive substances. Okay. Now if you see the rotational spectra of rigid diatomic molecule. So rigid diatomic molecule, rigid means what? During rotation, if there is no change in the bond length, if no distortion of bond length, that is called rigid diatomic molecule. For example, if you take C double bond O, during rotation, this bond length fixed, bond length doesn't change. That is called rigid rotator. That is called what? Rigid rotator. Okay, now we have to see rotational spectra of rigid diatomic molecule. Okay. So first we have to see what are the various possible rotational energy levels that we can get by solving Schrodinger wave equation. If you solve the Schrodinger wave equation for rigid diatomic molecule, you will get the expression for energy as h square by h by 8 pi square IC j into j plus 1, that is in centimeter inverse. Energy expression what we will get? H by 8 pi square IC into j plus 1. All these are constants for a given diatomic molecule. H constant, 8 constant, pi constant, C constant. I is nothing but what? Mu r square, bond length fixed. Masses are also fixed. Masses may not change during rotation. So moment of inertia is also constant. All these are constants. All these constants we are taking as B, where B is called as rotational constant. B is called as rotational constant. So the expression for various possible rotational energy levels is given as Ej is equal to Bj into j plus 1. B is equal to h by 8 pi square IC, that is called rotational constant, and J is called as rotational quantum number. J is called as rotational quantum number. Various possible values for J are 0, 1, 2, 3 and so on. And if you see degeneracy of each energy level, is 2J plus 1. Degeneracy of each energy level is 2J plus 1. First level degeneracy is 2 into 0 plus 1. Degeneracy order is 1. Second level degeneracy 2 into 1 plus 1. That is 3. That means second level, if you place sample in the presence of electric field, the second level split into how many levels? 3 levels in the presence of electric field. That is called what? Stark effect. In the presence of magnetic field, splitting is called what? Zeeman effect. Okay, second level, if you take, how many degenerate energy levels are present? 2 into 1 plus 1, that is 3. Third level, if you take J value 2, 2 into 2 plus 1, 5. 5 degenerate energy levels are present in the second level. Okay, so you just remember the expression for various possible rotational energy levels. That is Ej is equal to Bj into j plus 1. The possible values for J are 1, 2, 0, 1, 2, 3 and so on. What is the degeneracy of each rotational energy level? 2J plus 1. Okay, now if you see some of the allowed energy levels, we have Ej is equal to Bj into j plus 1. Okay, centimeter inverse. Now what are the allowed energy levels? And if you put G is equal to 0, then we get E naught as 0. So 0 point energy is 0. If you take J is equal to 1, E1, if you substitute 1 plus 1, that is 2B. J is equal to 2, E2, 2 plus 1, 3, 3 into 2, 6B. J is equal to 3, E3, 3 plus 1, 4, 4 into 3, 12B. If you substitute J is equal to 4, E4, 4 into 5, that is 20B we are getting it. So these are the various possible rotational energy levels for rigid diatomic molecule or rigid rotator. The gap, if you see, delta E, gap here 2B, here 4B, here 6B, here 8B. That means as J increases, what about energy gap also increases. As J increases, energy gap increases. The gap between any two successive energy levels is given as 2B into J plus 1. The gap between any two successive energy levels is given as 2B into J plus 1. For example, 0 and first levels. 0 and first level. J is lowest rotational quantum number we have to substitute. J value if you substitute 0, 0 plus 1, 1, 2B we are getting. If you calculate gap between third level and fourth level, J we have to substitute lowest rotational quantum number, that is 3 plus 1, 4, 4 into 2B, 8B. Okay, so as J increases, the gap between successive energy levels increases. This is the gap between two successive energy levels. Delta E is equal to 2B into J plus 1. Next one, selection rules. Okay, based on selection rules, we can give what? Intensity of spectral lines. Okay, intensity of spectral lines depends on selection rules also. What are the selection rules for pure rotational spectra? If you see, delta J is equal to plus or minus 1, and another one is the molecule has to possess permanent dipole moment, already discussed. Delta J is equal to plus or minus 1, plus for absorption, minus for emission. Plus for absorption, minus for emission. If you take, okay, some of the allowed transitions, okay, the transitions which follow selection rule, that is said to be allowed transition. The transitions which do not follow selection rule, that is called what? Forbidden transition. So if you take 0 to 1, that is allowed or not? Delta J is equal to plus 1, allowed. 1 to 2, allowed. 1 to 3, not allowed. Delta J we are getting 2, not allowed. Next 2 to 3, allowed. 3 to 4, allowed. So these are some of the allowed transitions according to selection rules. Which do not follow selection rules, those are called what? Forbidden transitions. Now 0 to 1, that is allowed transition. So what about energy absorbed during this transition? Energy absorbed is nothing but the gap between those two levels, that is E1 level and E0 level. What is the gap between E1 and E0 level? That is 2B. That means we get a signal at 2B centimeter inverse. Okay, whenever rotational transition, whenever we are applying microwave radiation, if rotational transition occurs from 0 level to first level, we will get a signal at 2B centimeter inverse. If the transition occurs from first level to first rotational energy level to second rotational energy level, where we will get the signal, and the signal is nothing but the gap we get the signal at, you get the gap between those two energy levels, E2 minus E1. What is E2 minus E1? 4B. Next one, 2 to 3, we will get a signal at 6B. 3 to 4, we will get a signal at 8B centimeter inverse. So finally, if you see where we are getting the signals, the signals are observed at, this I am taking for reference and is 0. This I am taking for reference, that is 0. We get a signal at 2B centimeter inverse. Next signal at 4B centimeter inverse. Next signal at 6B centimeter inverse. Next signal at 8B centimeter inverse. Like this we will get various spectral lines. And so spectral lines are observed at 2B, 4B, 6B, 8B. So the gap between any two successive spectral lines, the gap between any two adjacent spectral lines is what? 2B centimeter inverse. You remember this point. The gap between any two successive spectral lines for rigid diatomic molecule is 2B centimeter inverse. Okay, this is about rotational spectrum of rigid diatomic molecules. Okay, rotational spectra for rigidly diatomic molecule is characterized by what? Is characterized by a series of spectral lines at 2B, 4B, 6B, 8B and so on. The gap between any two successive spectral lines is 2B centimeter inverse. Okay, how to determine bond length based on rotational spectra? How to determine bond length based on rotational spectra for rigid diatomic molecule? For example, we want to calculate what CO bond length. For CO, we have to record what? Microwave spectra, rotational spectra, we have to record. For CO, first we have to record what? Microwave spectra. Okay, after recording microwave spectra, if you take gap between any two successive energy levels, what we get? 2B we will get. The gap between any two successive energy levels is 2B. From that 2B, we have to take what? Bn. So B is equal to what we have? H by 8 pi square IC. So from this B, we can get what? I. I is equal to what we have? Mu R square. So mu is known to us M1 M2 by M1 plus M2. 12 into 16 by 12 plus 16 in atomic mass units we have to substitute. Okay, mu is known to us. I we can get by using this equation. So bond length we can calculate it. So this is the procedure we follow to determine bond length. So one of the applications of rotational spectroscopy is what we can calculate bond lengths for diatomic molecules only. Here we are discussing by diatomic molecules only. Okay, first we have to record the microwave spectra. We will get 2B. From that 2B we will get B. So B is inversely proportional to I. All these are constants. If you substitute all those constants, we will get I. I is equal to mu R square. So from that we will get bond length. Next, if you see what is the effect of isotope on microwave spectra. What is the effect of isotope on microwave spectra? Okay, for example, we are taking C12O16 and I am taking C13O16. Carbon lighter isotope C12 I am taking and its heavier isotope C13 I am taking. Now is there any effect on rotational spectra or no effect on rotational spectra? If you see, okay. First if you take mu and mu is equal to what we have M1 M2 by M1 plus M2. Here mass here 13 we have, here 12 we have. So therefore reduced mass if you see mu C13O16 is more compared to C12O16. Okay, now I is proportional to what? Mu. So therefore I is less than I dash. How isotope affects rotational spectra that we are discussing. For that, if you see first reduced mass for both of these molecules, reduced mass is high for C13O16. Moment of inertia is also high as I is proportional to mu. Now what about B and A? B is equal to H by 8 pi square IC. We have B is inversely proportional to I. That means B value is greater than compared to B dash I. Okay. So B value for C12O16 is more compared to C13O16. Okay. Now if you see various possible energy levels, and what are the various possible energy levels we have? E1 is 0. After that E2 we got 2B. Next one 6B. Next one 12B. We got like this 0, 2B, 6B. Okay, 12B, like this we got. Here gap is 2B, next gap 4B, next gap 6B. As J increases, gap also increases. This is for C12O16. Now what about for C13O16? Same E1 is 0. What is the formula we have in energy? B into Bj into J plus 1. This is the expression for E and Bj into J plus 1 for C12O16. But for C13O16, what we get? B dash J into J plus 1. B dash J into J plus 1 will get for C13O16. But B dash value is small compared to B. B dash value is small compared to B. So therefore, we'll get below this 2B and below this 2B. So this is 2B dash. 2B dash. Next here we will get below 6B. This is 6B dash. This is below 12B and 12B dash. Okay. So here, in the case of C12O16, the signals are observed at what? 2B, 4B, 6B and In the case of C13O16, the signals are observed at what? 2B dash, the gap is what here? 2B dash, next one 4B dash, next one 6B dash. The signals are observed at 2B dash, 4B dash, 6B dash. So if you see, if you compare, this is just 0 I am taking for reference, 0 I am taking for reference. In the case of C12O16, we will get signals at 2B, 4B, 6B, 8B, and so on like this. 2B, 4B, 6B, 8B, like this. In the case of C13O16, we will get at 2B dash, 4B dash, 6B dash. So 2B dash value is small compared to 2B, so we will get like this. 4B dash value is small compared to 4B. 6B dash value is small compared to 6B. 8B dash value small compared to 8B. So this is 2B dash, 4B dash, dashed lines indicates 6B dash, 8B dash. Since here only 2 times it decreases, 2 times only we have, that's why small gap. Here 4 times, 6 times, here 8 times. The gap increases between 2B and 2B dash. 8B and 8B dash, the gap increases. Since here 2 times we have, here 8 times we have. That means there is an effect of isotope on rotational spectra. Like this, isotope affects rotational spectra. So the gap between the successive energy levels decreases, and the gap between successive energy levels decreases by using isotope, heavier isotope. Next one, how to calculate isotopic mass. Isotopic mass. So another application of microwave spectroscopy, is we can determine what? Isotopic mass. We can determine isotopic mass. For example, C12O16 we have, CXO16 we have. Okay, CXO16. We don't know whether it is C13 or C14, for example. Okay, I want to calculate heavier isotope mass. I want to calculate heavier isotope mass based on rotational spectroscopy. This is another application of rotational spectroscopy. What we have to do? We have to record rotational spectra for both the molecules. Whenever we are recording microwave spectra, we will get here the gap between any two adjacent lines 2b. Here the gap between any two adjacent lines is 2b dash. So from that what we get? B and B dash. Okay, the gap between any two successive energy levels is here 2b, here 2b dash. So from that we will get B and B dash. So now if you do B dash by B, B is inversely proportional to moment of inertia, so we will get what? I by I dash. I is directly proportional to reduced mass, so therefore we get mu by mu dash. So B dash and B values are known to us. B dash and B values are known to us, that we can get from spectroscopy, rotational spectroscopy. This data may be provided to you. B and B dash value may be provided to you. What is the mass of this carbon atom, heavier isotope, that we have to calculate it. So reduced mass for CO, this is for what? C12O16, this is for CXO16. So we know M1, M2 by M1 plus M2. M1, M2, that is 12 into 16 by 12 plus 16, that we have to substitute in atomic mass units. Mu dash means what? We will get reverse. X plus 16 by X into 16x. X plus 16 by 16x. So X we can calculate, and since B dash values are known to us, like this we can calculate X value. Okay, this is the procedure we follow to calculate isotopic mass. So this B and B dash values may be given to you. They may ask you to calculate Xn. So these are some points you may remember from microwave spectroscopy or pure rotational spectroscopy. Okay, one is Lambert's-Beer's law. Next one, classification of molecules based on moment of inertia. And what is the expression for rotational energy levels? Selection rules you remember. What is the degeneracy of each rotational energy level? That is 2J plus 1. What is the pattern of rotational spectra for diatomic molecules? How we will get? We will get series of spectral lines. The gap between any two spectral lines is 2b centimeter inverse. From that 2b we will get b. B is inversely proportional to I. From that we will get I. I is equal to mu r square. So bond length we can determine like that. Next, what is the effect of heavier isotope? If you use a heavier isotope, what happens to the gap between successive spectral lines? Decreases. 2b becomes 2b dash, 4b becomes 4b dash, 8b becomes 8b dash. And finally, how to calculate isotopic mass we discussed. Okay, this is about rotational spectra. In the next class, we will discuss IR spectra, vibrational spectroscopy. Okay, thank you.